So that's the system we're going to study. Actually, that's the system we're going to do it. Everybody will have a PID controller right here, and have a sensor, have a control element, which is a heating element, and control temperature in a small incubator, small shoebox. So this is the system we're going to, for this semester, for this class, PID control. And if you look at the chapter numbers I marked over here, right now we just did the first block, measurement. Actually, we did many blocks, processing a little bit, signal conversion, but the majority, 3 chapters, 6 chapters out of 3 out of 6 is for chapter 4, 5, 6 is a measurement. Next topic, we're going to cover chapter 7. That's what we're going to do today. And of course, we have chapter 9, 10, 11, and 12. So we have 6 more chapters. So we have finished. So we will got another 6 chapters right here. And chapter 12. So we will cover all the chapters from this textbook. So let's go right into chapter 7. Chapter 7, we're going to do the control element, this part, the control element. So what exactly is a control element? The author gave a little example right here. So you have to move, so you have motors, belt, motors, right here. More detailed, the author divided the control element, that one block, into 3 smaller blocks. So this was the control element, all 3. The first part of the control element we will talk about will be the signal conversion. The second part will be the actuator. The third part will be the final control element. So the author divided into 3 small components. So we will study the 3 small components. If you can see my notes, here is notes I prepared for today. This covers all the materials of chapter 7. I hope the document is good enough. I think it's good, but so the first topic we're going to talk about will be the signal conversion. The second topic will be the actuators. The third topic will be the final control element. You also add a final. Final control element. So let's look at the first topic for today, the signal conversion. What are we talking about signal conversion? First, an old topic is analog to digital conversion. You have analog signals, you have digital signals. You need to convert analog to digital, digital to analog. So that's the first type of conversion. That is not the main material for today. The second topic is about the pneumatic and electric signal conversion. So a lot of control systems, for a very good reason, use pneumatic signal. So what exactly pneumatic signal? That's 3 to 15 psi. So we prefer a signal pneumatic, which goes 3 to 15 psi. So how can we convert an electrical signal into a pneumatic signal, or a pneumatic signal into an electric signal? There are many different ways. The author put one method right here, give you an idea. So figure 6 on page 342. On page 342, let's look at this figure right here. So that's the electrical signal. The electrical signal will go to a coil. The coil will create electromagnetic force, which will pull the flapper up and down. So the flapper will be controlled by this 4 to 20 milliamp current. So it's a 4 milliamp current, the flapper will be all the way up. If it's a 20 milliamp, the flapper will be all the way down. So somewhere in between, the flapper will be somewhere in between. What that happens is the flapper will actually cover a little nozzle. The nozzle has an input with a three-way connector right here. So input pressure is 20 psi. And depending on the position of flapper, the output pressure will be 3 to 15 psi. So obviously, this thing need to be calibrated. So once that everything is calibrated, so 4 milliamp input current will create a 3 psi. Why 3 psi? Because a lot of pressure is released from the nozzle. And if the input is 20 milliamps, the output pressure with input still 20 psi, the output will be 15 psi. Why? Because less pressure is escaped from the nozzle, and more pressure goes that way. So this is one example of a signal conversion. This signal conversion is electrical to pneumatic. Pneumatic is preferred for many ways. One way is it's no electrical spark. You see, there's no electrical. So there are many ways to do pneumatics. Advantages for pneumatic signal. So that's why we do this conversion. We can also do the reverse conversion for pneumatic to electrical by, for example, a pressure sensor. When we talk about the sensors, we talk about pressure sensor, and that pressure sensor will be the pneumatic to electrical conversion. The last topic for signal conversion is actually power switches. That's a big topic. That's a subject which is see a lot of research and development and see a lot of progress in recent years. Power switches. So the power switches, basically, there's one type of power switches is mechanical. That is the power switch we're going to use in our project. So I'm pretty sure everybody know we are going to do a project for the last 5 weeks, last 4 or 5 weeks. So the power switch we're going to use in our project will be a relay. But there are other power switches, most likely 2 categories. One is called the diode. One is called the transistors. So right here, I circled 1, 2, 3, 4. Those are 4 different type of diodes used as power switches. The first one is called the silicon controlled rectifier. The second one called the GTO. The third one called the triac. The last one called the diac. So let's go through these 4 different type of diodes. They are all diodes. So what exactly is the first diode? This is the SCR. It's not like a conventional diode. It has a control terminal. So it's actually a controlled diode. It's not a, if you remember, I always like to use the plumbing to explain electrical. A diode is a one-way valve. So one-way switch. Conventional diodes do not have control. So this is an uncontrolled diode right here. That's a diode, but there is no control. It's an unconditional one direction flow. So if you have a flow in that direction, it's unconditional. This diode, SCR, is conditional. So even though you have a right direction flow, it's only able to flow if the control is active. Otherwise, this diode will not allow even the right direction. Obviously, there's no current can flow reverse. There's no reverse flow, but even the forward flow cannot go through until the control is active. So this is a controlled diode. We do not call it control diode. We call it SCR. SCR. So that's the first type of diode used as switches. Extremely common, SCR. The second one is called the GTOs. GTO. That is another diode. So that's GTO. It's a gate turn-off transistor, GTO. So the GTO is, this is how a GTO looks like. The symbol for GTO, it has a G, gate. And this is another diode. If you look closer, this is just another diode. The difference is it has a gate. So this gate will turn this on. It will also can turn it off. So this is an improvement over SCRs. SCRs can only turn it on, cannot turn it off, unfortunately. This GTO, this control gate, not only can turn the diode on, it can also turn the diodes off. So this is obviously, if you need one of those, you need to turn it off. You need one of those, GTO. The next one is a triac. A triac is look like this. This is a triac. It has two anodes. You see, those are two diodes connected upside down. That's one diode. That's a second diode. So there's a gate control this triac. This triac can just based on the diodes. One diode is upward, one diode is reversed. So triac can control both direction flows. So the current can go from this direction. The current can also reverse, forward and reverse. So the triac is a perfect switch for alternating. If you have a dimmer, everybody have a dimmer at home, right? In bathroom, in the bedroom, a lot of those dimmers are controlled by computers, cell phones, smart dimmers. Those are inside the dimmers. Final control the light, how much power goes to the light bulb. So that's the gate will control. The dimmer, obviously, some of the light bulb does not work with the dimmer because these switches just frequently turn the power on and off, and some of the circuits or appliances are not designed to have the power turned on and off like 60 times every second. It's actually turned on and off 60 times every second. So this is a triac. The half triac will be called a diac. So this is a diac. Diac is just two diodes. So this is a 4 diodes acted as switches, SCR, GTO, triac, and diac. And then there are many transistors, a lot of transistors newly developed. The author just gave 3 examples. This is a BJT transistor. That is the transistor we developed in the 50s, the earliest ones. And later we invented MOS, field effect transistor. So this is the oldest, this is the relatively new, this is the latest, IGBT. So let's look at each one. So the first one will be BJT. So BJT is a bipolar junction transistor. That's the fancy name for just the transistor. So most transistors are just BJT. So this is a BJT used as a switch. So that's electrical current to turn the switch on and off. By turning the switch on and off, a battery will provide power to the heater. So that can be exactly the situation in our project. We can have a BJT transistor. This is a battery. This is our heater for the incubator. So that is transistors. That's another example of transistors doing heating. Not only we have the transistors, we also have the MOS, field effect transistors. MOS field effect transistors. This type of transistor is considered better than previous one because it's voltage controlled. The gate is voltage controlled instead of this is current controlled gate. This gate is voltage controlled. That's why it's called field effect transistor. Field effect. The voltage controlled gate. Voltage controlled gate. That's very common, very popular. I have dozens of those here. We do the lab. When we do lab, when we want to control something like 20 watts, we use the MOS effect transistor. That's good enough to handle 20 watts, 100 watts, even thousands of watts, tens of thousands of watts, the big ones. The new player, relatively new player, is called IGBT. It's a bipolar transistor, so it is a bipolar, but the gate is insulated. So this is like a crossover between MOS and BJT. So if you cross over this guy with this guy over here, this and this, combine them, you get here. So the gate, so this is voltage controlled. That's the advantages, voltage controlled. But it's also bipolar. That is another advantage. So this part is bipolar. This part is voltage controlled. So IGBT is the latest player. It can do 400 amps. So it can turn 400 amp current on and off. What do they mean? 400 amp current. The average household current is 200 amp. So basically, this transistor can turn two houses on and off, 200 amps current. So that is the switches. What if I want to control 40,000 amps? Not 200, not 400 amps. 40,000 amps. To control 40,000 amps, the only way to do it is diodes. So that's the advantage of diodes over transistors. So diodes can control more current, more power. So if you want to control 1,000,000 watts, chances are the only components you can use is diodes. You cannot use transistors to turn 1,000,000 watts on and off. Those transistors, as far as I know, doesn't exist today. But maybe tomorrow. Maybe some of you invented one tomorrow. So there's a lot of research. There's a lot of development in this part. But so far, if you want to handle 1,000,000 watts, only diodes can handle 1,000,000 watts. Not only 1,000,000, even in the power delivery industry, they handle hundreds of million, tens of million watts using diodes, not the transistor. So this is our first topic called signal conversion. That's a big topic, especially the last one. Last one is a huge topic. I have a textbook here, an excellent book. I hope you guys, I hope we will offer this later. This is an excellent subject. Power electronics, that basically means electronics handles 1,000,000 watts. How can electronic devices handle 1,000 watts, 10,000, 1,000,000, 2,000,000, 10,000,000, or 100,000,000 watts? So that is our first topic. Second topic will be the actuators. For actuators, they also cover 3 different types of actuators. The first is the electrical, second the pneumatic, third is the hydraulic. We will go through each of those. The biggest, largest category is the electrical, obvious reason, because electrical is most convenient electrical. The other type is good enough also, but the electrical is so convenient. So for electrical, we have 2 different types. First is called the solenoid. The second is called the electric motors. So let's look at each actuator in a little bit detail. This is a solenoid. A solenoid is a linear mechanical actuator. So the position, they have a plunger. The plunger will basically push the target forward or backward. So solenoid is a very simple device. All you need is one coil. If the coil is energized, it will push the plunger forward. If de-energized, it will pull back by a spring. So it is a spring-loaded plunger, so it will forward and backwards. Of course, you can reverse the direction of current, and then you have two directional plunger. You can push forward and backward, both directions. So this coil can be positive current. You can reverse current. When you reverse current, the plunger will reverse direction. That is very common. For example, in the air conditioner units today, now winter is coming. You change from air conditioning to heat pump. How do you change from air conditioning to heat pump? You didn't go out to replace anything, right? All you need is flip a switch. What happens when you flip a switch? There is a solenoid inside your compressor. That compressor has a plunger with a four-way port. When you energize that coil, the plunger will push forward, and then your freon will reverse directions when the compressor turned on. What happens when freon reverse directions? In the summer, the freon is forward direction, so the heat will go from inside the house to the outside of the house. In the winter, you flip a switch, the freon will reverse direction. The heat will go from outside the house into the house. So you will get heating in the winter, and you will get a cooling in the summer. It's all accomplished because of one solenoid. You turn a switch, the solenoid will push the four-way port. That four-way port is designed so that the freon will be reversed direction. The compressor is not reversing direction. So compressor is always one direction, but the direction for freon is reversed during summer and during winter. So that's our first one, first actuator. The second type of actuators, we talk about the motors. When we talk motor, we have so many motors. We have a DC motor, we have AC motor, we have a newcomer, which is called brushless, and then we have a step-in motors, and endless, with people still developing new type of motors. The most common are those 4 different types: DC, AC, brushless DC, and step-in motor. Let's look at each a little bit detail. This is a DC motor, so that's battery powered. So there's a commutator. The function of commutator is reverse the flow of current direction. So the torque is always one direction. Otherwise, the torque will alternate in directions. So this is actually a converter. Convert DC to AC. So the coil right here will be AC current. Because once you flip the direction, the direction of current will also flip over, reverse. So DC power change to AC current. That AC current will create a constant torque. So that's a DC motor. You have 3 different type of DC motors. If you're interested, you can read all DC motors. That is the series. That is the parallel shunt DC. That is the compound, which has a serial and a series and a parallel field coil. So you have potentially 3 different types. What about this? This is called a permanent magnet. This DC motor is permanent. Permanent magnet is for small powered motors. I have many. So if you have a printer, inside you'll probably have 3 or 4 permanent magnet DC motors. So this is a permanent magnet. But permanent magnet generally cannot be very larger power. So if you need, for example, 10,000 watts, so this cannot be 10,000 watts. If you need 10,000 watts or 100 watts or 1,000 watts, you need one of those. So there's no permanent magnet. Instead, the electrical coil will create magnetic field. So this is how the electromagnetic field is created. And then this is the rotor coil. This is a parallel. So alternatively, you can create the magnetic field through a field coil, which is in parallel to the armature, or in series, in parallel, or a combination of series and parallel. They all have different characteristics. Most notably, the torque and RPMs are different. The starting torque are different. For example, this one has the highest starting torque. Some applications require high starting torque. This one has a high RPM. So, for example, if you have a rotor, I'm pretty sure some of us are woodworkers. I'm not a woodworker, but I have 2 or 3 routers. I have a lot of tools. I actually work on woodworking, but I don't have a lot of time. But when I have time, I really enjoy it. So I have 2 or 3 routers. Those are the motors inside for the routers. So what the router does, it has a very high starting torque. Also, the RPM can go to, what is RPM for a router? Never know. 11,000, right? 11,000. That is only can be accomplished by this type of motor. 11,000 RPM. So that is, how about RPM for the second type of motor, AC motor? The second type motor, AC motor, the RPM highest is 3,600. So that is your air conditioner units, your dishwasher and dryer, a lot of appliances use AC motors. They don't need a high RPM like 11,000. They just need 1,100. So for 1,100 RPM, you have a AC motor. So how does the AC motor works? AC motor was invented by Tesla. This motor is still the most important motor in everywhere, either the household appliances, industrial applications, more recently electric cars. So all those electric cars are actually driven by a Tesla motor, invented by Tesla. So this is, we call it AC induction motor. So AC induction motor, the author didn't pay a lot of coverage on AC motor, so we just kind of do what the author does. So the AC motor is the most important motor. It's toughest, it's lasts forever, low maintenance, extremely low maintenance. AC motor, all you need is to take care of the bearings. I recently, for the past couple of years, I replaced at least 5 or 6 AC motors. Every one of those fails. because the bearing. So if you have AC motor around your house, make sure every 2 or 3 years, put some grease or oil, whatever, into the bearing of those AC motors. Generally, people never pay attention. So after about 10 years, the bearing is all give up, or it will wear out. That's how the AC motor fail. With proper maintenance on the bearing, all you need is every 2 or 3 years, regularly you repack, put some grease or put some oil. It will last forever. I mean, really, forever, almost. The next one is step-in motor. Step-in motor is why AC motor became so popular recently. Because of this, this is the only reason why AC motor, all of a sudden, AC motor became so. It was the most important motor. After this, it became even more important. This is called rectifier inverter. So this is 60 Hertz AC, and they change it to DC. After convert to DC, it will convert it to AC again. So AC, DC, AC. Well, you might wonder, are you crazy? Because AC and the output is AC. So it's AC, DC, AC converter. The AC motor will be connected right here. What's nice about this is the frequency of the output AC can be controlled by computer. So computer can just turn on those switches. Every one of those are switches. If you look closely, one switch, 6 switches over here, those are the diode switches. How about the inverter? Inverter is another 6 switches. That's all we need, 6 switches. And by the computer, by control exactly when to turn on those switches, almost like magic. The input converted to DC, and then DC convert to variable frequency. This is called a variable frequency drive. So the output frequency will go from 0 Hertz to, for example, 400 Hertz. Input will be 60 Hertz. Output 0 to 400 Hertz. And why do you want 0 to 400 Hertz? That because RPM of AC motor is directly determined by the frequency. This is the equation right here. So the RPM of, that's RPM. The RPM of AC motor is a frequency divided by number of poles. A number of poles is how we design the AC motor, so this is constant. So if a frequency is 0 Hertz, RPM will be 0. If frequency is 60 Hertz, RPM will be, for example, 1100. If frequency is 1200 Hertz, not 1200, 120 Hertz, the RPM will be doubled. So that is why AC motor became so popular, because now all of a sudden we can control the RPM of AC motor extremely accurate. That's one reason. The other reason is by control the timing of these switches, the power can flow both directions. The power can go from the DC, that's electric car. So if you have a battery here, you don't even need this part. So if you have a battery here, that's the electric car, the power can go from the battery, right, which is right in the middle, to the motor. That's when you accelerate or driving. And if you want to brake, just by control the timing, the power can go from the motor, which became a generator, generating power, charging the battery. So the power can flow forward, backwards, and that is perfect for electric cars, electric trains, high-speed trains around the world. Many, very, very common. In the United States, they also have high-speed trains. I think from So all those high-speed trains is so efficient that because of this technology, the high-speed train is driven by AC power, of course. High-speed train is driven by single-phase AC power. So we don't even have to have a three-phase AC power in the left. All we need is a single-phase AC power because all we need is DC right here. So single-phase to DC, DC to three-phase AC. That is electric, high-speed electric train. The next one is a stepper. Stepper is also a very common motor. Stepper motor. Stepper motor is generally considered a digital motor because it's always controlled by a computer or digital circuits. So that's how a stepper motor does. That's one example of a stepper motor. This stepper motor will rotate 15 degrees per step. So that means every time the computer sends out a command, this motor will rotate 14 degrees forward or backward, 14 degrees. So that's why it got the name stepper. Stepper means it's not continuous. Unlike the previous motors, it's rotating 0 degree to whatever degree continuously. The stepper motor is only, in this case, 15 degrees forward or backward, cannot do 4 degree. Actually can do 4 degree with the proper circuits, but generally we just use the stepper motor as it is. So 15 degree, for example, or 3 degree, or whatever stepper motor. Depend on the number of poles, depend on internal construction. So some stepper motors do 15, some do 3, some do 1.5, whatever degree, every step. So this is an example of a stepper motor. Generally, stepper motor has 2 coils. That's all we need to know. Stepper motor has 2 coils. We need to energize. This one has 2 coils with a ground. Another stepper motor, 2 coils without ground. So some stepper motor have 5 wires, 1, 2, 3, 4, 5. Some stepper motor called the bipolar has only 4 wires. This Wednesday, we will do a demo for all the different types of motors we covered here. So we will do a stepper motor also. So that is 3 types of motor. The author did not cover the latest motor called the brushless DC motor. What exactly is the brushless DC? Some of you work in the industry may know it means expensive, right? Brushless DC, even the consumer electronic. For example, if you have an inductive AC motor in your blower, it's $50. If you have a brushless DC, brushless motor in your blower, in your air conditioner furnace inside, some of the modern furnace use brushless. So if you have a very high-tech furnace, your motor is out. What happens is a $300 brushless DC motor, $300 right here. So why we do that? $300. Why don't just use a $50? Actually, a lot of people do a retrofit. I was on YouTube watching. A lot of people just don't like brushless DC. They retrofit it into an inductive AC motor. That's another story. But why we use brushless DC? One word. It's control and efficiency. 2 words. The first word is control. For brushless DC motor, we can control the RPM and the torque extremely accurate. RPM and torque through a computer. So that's why it's so expensive, because the majority of brushless DC motors are controlled by a computer. And computers are dirt cheap. Computer is just $1. But those companies charge you $300 because they want to make money. So this is control. The first word is control. RPM, the torque, can be controlled very accurately. Second word is efficiency. It will save power, use less amount of power. So for example, if you have a power tools, cordless, the cordless power tools, battery, if you buy a new cordless drill or cordless drive or cordless whatever, if it's brushless DC motor inside, the manufacturer always claim it will last, the battery will last twice as long as the DC motor. I don't have any brushless DC motor tools, so I don't know. But that's what the claim is. They may be true. Use only half the power of the other type of motors. So not only they have high torque, they have RPM can be controlled very accurately. It also saves power. So that's why brushless DC motor is a new player. It's actually not a new player. It's a 30 years old, 40 years old player. But it was so expensive. The computer is so expensive. Nobody uses it. Now the computer are getting cheaper and cheaper. So it's gradually, it's everywhere. So the brushless DC motor are replacing a lot of motors. For example, I saw a brushless DC starter motors for cars. Right now, all the starters for the engine are just DC motors. So I saw a little bit expensive, but almost similar priced brushless DC starters. That will be perfect. Why perfect? That's the third thing about brushless DC. It will last, suppose, forever. Because there's no brush. If you work on cars, the conventional DC starters will fail because of what? The brush is running out of brush. The brush needs to be replaced every, for example, 1,000 hours. So those brushes are made of very soft material. After about 1,000 hours, they just wear out. And that's a huge maintenance problem. So brushless DC, not only it's control, it's saves power. The last thing is last forever because low maintenance, no brush. Unfortunately, this thing doesn't last forever. The reason is the computer. They make it so complicated, the electrical circuit so complicated. That is why a lot of people do retrofitting. So their brushless DC motor supposed to last forever. Unfortunately, after about 10 or 5 years, they also fail. So cost is $300, supposed to save you a little bit of electric bill, a couple cents maybe every month, maybe a couple dollars every month. But if it doesn't last forever, you have to replace it after 5 years. It doesn't make any sense at all because the $300, you didn't save $300 electric bill at all. So it's an issue. It's an issue. Reliability of this motor, because the computer, the electrical components make it so complicated. In theory, it lasts forever. In practice, it's not forever. Nothing is forever. So that's the motors. So we talk about the 4 different types of motors. The last type is not in the textbook, but it's a big new player coming. Then we have pneumatic actuators. They also talk about pneumatic actuators. Makes sense. Pneumatic, the pressure change to mechanical. So this is a pneumatic actuator, linear. So the pressure 3 psi, 15 psi. The cylinder, the diaphragm will move up and down. and this plunger, this rod will push whatever need up and down. So that's pneumatic. Pneumatic is very good, but is not very powerful. So it can be good to turn on a valve on and off. But what if you want to have a 10,000 pound? So if you want 10,000 pound actuator, hydraulic, so pneumatic cannot do 10,000 pounds, maybe 100 pounds, maybe 10 pounds actuator. If you need 10,000 pounds, it had to be hydraulic. So that is an example of a hydraulic actuator. This actuator actually pushed the linear direction forward, backward. So this is called a linear hydraulic motor. Linear hydraulic motor, because the mechanical direction is left and right only. So this linear hydraulic actuator can push, for example, 10,000 pounds, because hydraulic has a huge pressure, very high pressure. Hydraulic pump can be very high pressure, and the linear actuator can push 1,000 pounds, 5,000 pounds, 10,000 pounds. The big ones can have a lot of power. So this is a linear motor. I recently replaced the transmission for my tractor. I have a lawnmower tractor, ready mower. The transmission fails. The transmission fails because the motor fails. The transmission, inside transmission, is called a hydrostatic transmission. The reason it's called hydrostatic is because the transmission is all hydraulic. It's actually very smart design, simple design. It's a very popular design. So you have a belt-driven. So the engine power drive a belt. The belt drive a pulley. The pulley will drive a hydraulic pump. So the hydraulic pump will pump in hydraulic. And then on the other side of the hydraulic will be another hydraulic pump acted as a motor. So the hydraulic pump can be either work as a pump or a motor. If you have mechanical energy, it will be a pump. If you have hydraulic energy, it will be a motor. So inside the transmission is just two hydraulic pump. One acted as a convert mechanical power to hydraulic power. The other convert hydraulic power back to mechanical power, the RPM, the rotations. The output will be driving the two drive wheels, two rear wheels of my lawnmower. So my lawnmower, those motors wear out. Unfortunately, only after 200 hours of. So that's a huge problem for those riding mowers. It only lasts 200 hours. They tell you the transmission is not serviceable. So the transmission there's no service. So it fails about 200 hours. Unless you service the transmission. That I hope I serviced my transmission. By service only means to replace the oil inside the transmission. Replace the transmission. Replace the fluid. So if you never replace the fluid, that transmission only lasts 200 hours. So if you replace the fluid, it may last maybe 500, 700, or 1,000 hours. Unfortunately, the manufacturer just wants you to buy another one after 200 hours. It doesn't matter which brand. As long as it's $3,000 or less, they all same thing. The higher priced ones may be a little bit better, but Anyway, this hydraulic pump, hydraulic motors. Hydraulic motor can be linear. This is linear. Can also be RPM rotations. So the last topic for this chapter 7 will be the final control element. Final control element, they also cover the mechanical, electrical, and hydraulic, fluid valve. So let's look at the 3 examples. The author covered this topic with a couple of examples. The first one is the mechanical control element. The mechanical control element is just this flapper. So this flapper, that's the actuator. The actuator will push the flapper. The flapper is the mechanical control element. So the mechanical control element is just that. It will control how much grain is dumped to the conveyor belt. So you have a conveyor belt system, and how much grain is dumped to the conveyor belt is controlled by this control system. So this is a PID control, for example. It doesn't have to be PID control. It turned out PID control is the most popular one. So a PID controller, sensor, and then whatever flow rate you want. For example, I want 100 pounds per minute, or 100 pounds per, or 200 pounds per minute, or 1,000 pounds per minute. Whatever the flow you want it, the operator will enter the set point. This is called the set point. The operator will set the set point, and the controller will automatically control this flapper. So just 200 pounds of grain will be dumped per minute. That is a control example. The project we will do will be identical. The only differences is the sensor is different, the control element is different, the actuator is different, everything else is the same. So if you mastered the PID controller for a temperature, then it's everything. It can be a flow, can be a humidity, can be a pump, can be anything. The only difference is the actuator. This part is different. The sensor is different. But everything else is the same, identical. The second example is electrical final control element. The electrical final control element will be this this motor, this roller. I would think this is also mechanical, but it also says electrical, so let's call it electrical. Oh, mechanical. Oh, this is also another example of mechanical. Okay, I think the author is correct. The author gave another example of mechanical final control. So that's the second example of mechanical control. The motor is the actuator. The actuator will push a roller. This is the roller is a final control element, which is a mechanical. This roller will control the thickness of paper. That's nice. So the paper will have the thickness of your paper will be consistent. The sensor is a position sensor called the LVDT. Remember the sensor we talked about? LVDT sensor. So LVDT sensor will sensing the thickness of paper, and this PID control will control the electric motor, and then push the roller. So the thickness will be consistent every day, every month, every year. It doesn't matter when the paper is made. It will be always the same thickness. The operator will enter the thickness of your paper from the controller right here. So again, we have this example of a PID controller in an industrial application. And the engineers work at here are paid at least, for example, twice my salary. So in the industry, they have a very good salary in these engineers. So what does that mean? That means if you know how to tune a PID controller, you have a proven track record. You can make a career for this type of industrial applications. They pay a very good price because a lot of money is involved to do it right. With our project, you get a little bit of experience. That's not enough. To be able to make a career, you need years of experience because every different actuator, every different final control element, every different process, every different sensor, and all the signals involved, the digital analog signals involved, the strong electrical signal, the motors involved, the mechanical component, the pneumatic, hydraulic system. Oh my, this is extremely complicated. So that exactly means to be a good control engineer. So some of you may say, oh, I want to be a control engineer. To be a good control engineer, you need a lot of knowledge about everything. A lot of knowledge about it. It's not book knowledge. It's not something you just learn from colleges or universities. It can only be learned by working in this industry for years and years. And we do have very good students who are straight A students, unable to troubleshoot, for example, one wire is broken from here to here. The system doesn't work, so what exactly is the problem? It can be very intimidating, but it can only be one wire is broken from here to here. And if you spend a week cannot troubleshoot and solve the problem, and then they hire a consultant to come over, and that consultant have some kind of experience and solve the problem within an hour, and consultant got $10,000 just for an hour work, and you lose your job because you didn't solve the problem for a week. So if you know how to do that, that's experience. The next example will be the electric final control element, electric. So this is a huge system, again, industrial application. That can be 1,000,000 watts motor, right here, 1,000,000 watts. Why do we need 1,000,000 watts? Because this thing can be, for example, as big as your house. So this can be a huge oven. And we are rotating this through gears, through a motor and a gearbox. And we have a temperature sensor. We want to control the temperature. For example, you are cement manufacturer. You are making cement. So you're dumping raw material into this thing, and then the motor will drive it, and then I think you need a fire also, some kind of fire. Anyway, everything has to be controlled. Without control, you cannot have cement. You cannot have a good quality product. If you want to make a good quality product, everything needs to be controlled perfectly. So that is another control system. So the operator will set, for example, 10 RPM. Why 10 RPM? Why not 1,000 RPM? You cannot do 1,000 RPM. This big house. 10 RPM or 5 RPM, whatever RPM you want to do. The RPM is decided by the temperature sensor. If it's too hot, you overcook your material, right? You do not want your material to be overcooked. How to prevent overcook? You roll it a little bit faster. So you got your material away from the fire a little bit. So, let's assume the fire is right here. So you have your fire right here. So if you rotate it faster, you cool it down a little bit. You prevent overcooking your material. So that's a temperature sensor. That's the motor. The temperature sensor will decide how fast you want to rotate this. So the product came out of the other side will always be perfect. That is another example. So this can be a PID controller. Why PID controller? Because in the industry, whatever works, as the simplest thing works would be, you do not want the fancy, overcomplicated devices. In the real world, keep it simple. The PID controller is proven to be not only get the job done, it's proven simple. Simple and get the job done. So if it's simple and get the job done, why bother to use anything else? So PID controller. I have a PID controller. The project I already completed. I was amazed how accurate the temperature in my incubator is. Up to 0.1 degree. They don't even change that number. You don't even change. So if I set the temperature to 75.9 degree, it will be 75.9 almost forever. Never change. Of course, in the industry, it's not like an incubator. For example, always raw material is coming in. So there's always a gate open and close. So that's but anyway, the PID is pretty good. Good. So the last, this is another example. They also did PID controller, control the temperature. Again, temperature control. This is another temperature control. The PID controller will control how much, for example, steam, the heating coil. This is an electrical actuator. The actuator, not electrical actuator, the electrical final control element. The final control element is an electric heater. So that's the last example. Electric heater as the final control element. This is the same as our project. So our project will be identical to this one. The only difference is we have a shoebox instead of heating vessel. This is a reaction vessel in the industrial application. We don't have a reaction vessel. We have a shoebox. The heating element is inside the shoebox. Is the final control element. The last topic for this final control element. So we covered the mechanical, we covered the electrical. The last final control element will be the flute valves. Flute valves is very, very common. Majority the flue valve we use are manual. So that's the manual flue valve. So we rotate this stem up and down. What happens when we manually change up and down is we change how much flow. So just like we're taking a shower, for example. When you're taking a shower, you want to control how much water. Some people like a big shower. Some like saving some water. That's mechanical, manual. But in a control system, this is automatic. So it's like a shower. So when you're having a shower, instead of you control how much water flow, the computer will control how much will flow. So the computer will have a control signal. The control signal will control how much is the flow. So when you enter the shower, you said, today I want 1 gallon per minute. Yeah. And tomorrow you want 2 gallon per minute. So if you want a really fancy shower, you can do that by having a PID controller control the flow of your shower. The final control element will be this valve. It will control the flow of the shower. There are different types of valve. They are determined by how we machine this part. This part called plug. the plug can have different shape. By control how the shape of the plug, we can make a valve, which are called linear, quick opening, or equal percentage. So that is obviously for industrial applications. That's not for your shower. Generally, people do not care about your valve is linear, quick opening, or equal percentage. Nobody cares, right? But in the industrial application, they potentially require that. So they require a valve which open and closing either linearly or quick opening, or this can be a quick closing, or we call equal percentage. So this is done by how we machine the plug. The shape of your plug determines this. The shape of your plug. In the industrial setting, the size of your plug also matters. Size. So this is a table tell you how to calculate the valve size in inches. That's the equation to calculate. So if you work in the local companies, they do some pipe fitting. When you do pipe fitting, the first thing you want to decide is the size of your pipe, right? It's 1-inch pipe, 2-inch pipe, 4-inch pipe, 8-inch pipe, right? You have to do it picking the size of your pipe for a reason. Some that's based on experience. That's good enough. But sometimes you may want to impress your boss. Based on experience, it's 2-inch pipe, but based on my scientific calculation, we can save some money, just use 1.5-inch pipe. You may get a raise, maybe impress your boss that way, because based on calculation, you may get fired because it doesn't work. So this is just generally the theory is the guidance into the field, into the reality. So this equation is good, but what final decide is what works in the field, in practice. So again, this is another issue about control engineers. You need book knowledge. You need a lot of book knowledge. That's why you're here. You are taking this class. You need some knowledge. That knowledge only can get from the textbook, from books. And that's not enough. You need a combination of book knowledge and hands-on experience. That's all we want to cover for today. So today we have one chapter, and I summarize this whole chapter through this one-page notes. So if you want to get a big picture of what exactly do we covered today, so we cover 3 topics. Each topic has multiple subtopics. And that's chapter 7. We will cover 5 more chapters. We have 6 weeks. Actually, this including this week, we have 6 weeks. So we have 6 weeks left. We have 6 chapters. So now you know what we're going to do. The end of semester, till the end of semester. So today we have this. Next week, last week. So we have 6 weeks, including this week. We have 6 chapters. And then we have a final. And then we will have Thanksgiving, right? We will have Thanksgiving. And then we have 2 months of winter break. I hope everybody will enjoy. And then I hope everything will be good, and see you guys in spring semester. But nobody knows. Nobody knows. Okay. All right. I'll see you guys. Any comments? Anybody want to say something about?
Well, this is very interesting. When are we going to actually put our project together? Because I still need to get the shoebox.
Shoebox. Okay. Did you buy another shoe?
No, I still need to get it. So yeah.
Okay. That's a very good shoebox. Anybody has a shoebox to share with Craig? I have a lot of shoebox. If you don't have one, I can give you one. Another way, did you go to like Aldi and some stores?
I went to a few different stores. I got a big box, but not a small shoebox size.
You can make a smaller one out of a big one.
Yeah, probably.
We are engineers. If you ask your boss this, so we should be able to solve all problems as engineers. Yes, cut your big box up and make a smaller one using duct tape. This is something I made this weekend. This is a wood burner. I have a lot of tree branches. Every year I have so many. I just burned it out in my yard. It's a huge waste of wood, and I do not have a fireplace. So I was thinking, how can I just use those for hot water? So that's what I made. If you can see this, I have a coil made of copper piping. That's the heating coil. So if I make a fire, this water will heat up. And it will go to this place. I will have hopefully tonight. I'm going to have a hot bath outside in my backyard. And if you bring some beers, maybe that's good.